Friday in lecture, all of you out in webland should come physically and bring a pencil, because you're going to fill out a course evaluation questionnaire that the department uses to actually make decisions about courses and promotion and all that. So it matters. And besides that, you get a point toward your grade in this course for doing it. An out-and-out bribe to get you to actually come, because there's been a historical problem about students not bothering to do evaluations, and that's bad. And so since we started giving out points, people actually turn up. Somebody came up and said, oh, but I can't do it because the survey is being run by Eta Kappa Nu, and if you have a problem, take it up with them. But try to be here. And the other thing is, I got an email about, did we notice how badly everybody did on midterm 3? Yes, we did notice. We're a few points below the historical average. Don't panic about it. My policy is not to make point adjustments on specific assignments, but to wait until the end of the semester. Because usually, you know, something is easy and something is hard, and they all balance out. But if that isn't the case, we'll do the right thing. OK, enough for administrative things. What we're doing this week, the rest of this week, is talking about 2 different variants of the metacircular evaluator. And you're making a third one, which is the logo interpreter. So let me actually start by saying, with respect to the final exam, you are expected to understand but not memorize the code of the plain metacircular evaluator that we looked at earlier, I guess last week. And you're expected to understand the stuff you did for the logo interpreter project 4. Again, not memorize, but understand how that works. For these variant evaluators, you are not expected to know about, for the exam, the details of implementation. I'd like you to get the general idea, and I'd like you to understand how they behave differently to a user. So, you know, today we're looking at the lazy evaluator. A fair exam question might be, this procedure here, does it give you a different answer under the lazy evaluator than under the plain scheme evaluator? That kind of thing. But not modify the lazy evaluator so that it, no, we won't do that. If we do that at all, it will be on the plain metacircular evaluator. OK. This is actually detailed in, in the course reader, volume 2. There's a 1-page thing called exit handout, which is end of semester information, and it's time, you know, for you to read that. Not right this minute, but you know, this week. It's time to read that. OK, so back to thinking about streams. And one of the problems that the book does, let me skip past the integers, you understand that. One of the problems the book does is to make pairs of integers. So here we have a bunch of lists of length 2 with integers, and the particular application the book had in mind, they don't care about the order. So they only generate the ones where the first number is less than or equal to the second number. So there's a pair 3, 5, but there isn't a pair 5, 3. So it looks like this sort of diagonal picture. And the book does it this way. It says constream. So pairs is a procedure that takes 2 arguments, which are streams, S and T. And the idea is we're going to say pairs, integers, integers. OK? So constream list stream car of S, so that's 1, because we're starting with the integers, stream car of T. So that's this little pair 1, 1 that's in a yellow box all by itself. And then interleave stream map lambda x list stream carve s x. Stream carve s is 1. So we're making a list 1 blumph for all values of blumph starting with 2 because of the stream cooter. This stream cooter right here is why you only get half the possible pairs. So we take 1 and pair it up with everything. No, I take it back. It's not why we get all possible pairs. It's why 1, 1 isn't included in this yellow stripe across the top. Because we have 1, 1 done separately, so we don't want to do 1, 1 again. We want to do 1 lump starting from 2. So that's the second piece. And then the third piece that we're interleaving with is pairs stream cooter S, stream cooter T. That's why we only get half the possible pairs, because we cooter both of them at once. So we're going to get, for the recursive call here, all the pairs from 2, 2 on down. Okay? Now, Lewis Reasoner in exercise 3.68, which I think you did, comes along and says, I don't get it. Why do we have to have 1, 1 as a separate thing all by itself? Why can't I just take the entire first row and interleave that with the recursive call? So Lewis agrees about the recursive call to pairs with stream cooter, but he wants to map lambda x list stream car s x not on stream cooter of t, but on t. So he's going to get 1, 1, 1, 2, 1, 3, all in one step. Okay? And so the exercise, of course, asks, why doesn't this work? And how can we fix it? So why doesn't it work? Come on, somebody. Why doesn't it work? Why doesn't Lewis's version work? Yeah. Interleave evaluates both arguments. So it's because he didn't have a con stream, right? Because con stream is the thing that delays its second argument. Interleave doesn't. So he has to do a delay of the recursive call in order for it not to work. I should have seen every hand up, you guys. You all did this exercise, supposedly. You all should have read the solutions for this exercise. You should have all said, oh yeah, I remember that. But you didn't. So, nag, nag. Okay, so that's Lewis's version not working. And we can fix Lewis's version this way. Instead of calling interleave, so we're doing what Lewis wants to do. We're only having 2 chunks instead of 3 chunks of this picture. So the whole front row is one thing, but we're calling interleave delayed instead of calling interleave. And this is the same. This stream map is exactly like Lewis's version. And this is almost like Lewis's version, except that there's an explicit call to delay in it. Okay? So we're explicitly delaying the recursive call, and so we don't get into the infinite loop problem that Lewis had. Interleave delayed, down here, looks just like interleave, except that it calls force on the delayed argument. It's only S2 that's delayed. That's why the arguments are, the formal parameters are S1 and delayed S2. So we know to force delayed S2. Oops, not what I meant. And then constream stream carve S1 onto interleave delayed of force delayed S2 and delay stream cooter S1. So when you do interleave, you reverse the arguments S1 and S2 in the recursive call. So that's how you get the interleaving of one and then the other. So here we're using explicit calls to force and delay in order to solve Lewis's problem. So now, here in chapter 4, what they would like you to understand is that for once, Lewis actually had a good idea. The thing that Lewis wrote is correct as a description of the result that we want. Okay, it's absolutely true that this chart consists of its first row plus the rest of it. And Lewis has an expression that does compute the first row and an expression that does compute the rest of it. And he's putting them together correctly with interleave because he understands that if they're both infinite, you can't say append this, that. So Lewis understands all that. The only thing is he's missing something that's a restriction in the implementation of streams. Really, it would be better if Lewis's version did work. That would be a better implementation of streams, okay, so that you just wouldn't have to worry about it. There's a name for making it work Lewis's way, where things get delayed without you worrying about it. What's it called? Yeah. No, there's an official name and you learned it. Yeah. Thank you. Normal order evaluation, right? That's what it means. What is normal order evaluation? You don't evaluate actual argument expressions until you really, really need them. So you pass in argument expressions instead of passing in argument values. Except, as we now know from looking at the implementation of streams, you don't just pass in the expression as a piece of text. You wrap a lambda around it so that you remember the values of variables as they're being used in this expression, because when we get around to evaluating it, those variables might not exist in the environment that does the forcing of the delayed expression. So we actually say lambda, open paren, close paren, bloop, and maybe we even memoize it. Okay? So normal order evaluation would solve the problem. Now, back when we first learned about normal order evaluation, we said, well, you might not want to do that because if you have a normal order evaluator and you define square x to be times xx, and then you call square with some big complicated expression, that big complicated expression is going to end up being evaluated twice instead of once, and that's inefficient. But since then, we've learned about memoization. So we now know that you can do a normal order evaluator with memoization, and you do square x to be times xx, and you send in an expression, and that gets evaluated the first x that we see, and then when we come to x again, we already know what the value is because that expression was memoized. So that eliminates the efficiency objection to normal order evaluation. In fact, sometimes normal order is more efficient because maybe we never get around to using some particular argument, in which case we shouldn't bother evaluating it. So if normal order is going to turn out to be more efficient once we do memoization, why doesn't everybody use normal order? When you were studying streams, what was the problem that came up that made things a little weird? Streams. Oh, man. Okay. Remember they did some stream problems, and what they put in the coder and the thing that was delayed was print this or set bang this to this plus 1 or that sort of thing. And if those got evaluated in an order that wasn't what you were expecting, things printed out the wrong order, or maybe things printed twice or something like that. Remember that? Okay? So how did we deal with that problem at the time? We said streams should be used if if you're doing functional programming, where you're not doing anything with side effects, you're not changing the value of anything, you're not printing things out, all you're doing is computing functions. If you're computing functions, then it doesn't matter what order things happen in. Okay, this was also the big strength of MapReduce, right? That if you're computing functions, you can parallelize things very easily. That's not true once you start set banging variables, as we saw back in chapter 3 with serialization, parallel execute and make serializer and all that. So the actual state of affairs in programming languages right now is that there are some purely functional programming languages, languages that do not have anything comparable to setbang in the language. So ML is a very well-known example, and Haskell is another one that professors tend to like. In purely functional languages, they do use normal order evaluation. And they do it precisely so that you can get infinite streams and stuff without having to think about it, and your programs always work. Okay? Scheme is an attempt at supporting multiple programming paradigms. And that's because, well, it's partly just because of the history of who made the language and stuff, but it's also because it's turning out in practice that very often the best solution to a big programming problem is not to be purely in this paradigm or purely in that paradigm. So very often there'll be whole chunks of the program that really are functional in nature, and those are best computed functionally. And then there'll be other parts of the program that are, for example, interacting with the user, and those things are best done object-orientedly, and so on. Okay, so Scheme tries to let you do everything. Because of that, it does have mutation in the language, and because of that, it can't just use normal order all the time. Because if you use normal order all the time, you get funny effects of reordering the sequence of events in the computation. Things don't mean what they look like they mean. And instead, what we have is the ability for users to define special forms, the way we defined constream using delay. So if you're solving a problem where normal order evaluation would be really helpful, you can arrange it for yourself. Okay, so what we're going to do here is modify the metacircular evaluator to be a normal order evaluator. And again, you wouldn't really do that unless you took out setbang in practice, but it's interesting to do as a exercise in understanding the evaluator. Okay. Okay, here's the lazy evaluator. It's actually what's in this file in the library is just the parts that are different from the regular metacircular evaluator. So it starts down at the bottom of the screen here by loading in MC eval, and then it's going to redefine certain procedures. In particular, it's going to redefine eval and apply. So let's look at why that is. Here's eval. So self-evaluating expressions are still the same. It returns the value of the expression. If you get a variable as an expression, you just look up its value. That doesn't change. If it's a quote expression, you just take its cater, which is what text of quotation is. And that is to say the thing that comes after the word quote. So if it's an assignment, we do eval assignment, although again, that's the line we would leave out if we were really defining a functional language. If it's a definition, we eval definition. If it's an if, we eval if. If it's a lambda, we make a procedure with the parameters in the body and the current environment in the right bubble. That's all the same. Begin, that's the same. Con, that's the same. Here's what's different. What if it's a procedure call? Well, what we do in the regular metacircular evaluator, let me actually, okay, so down here is the ordinary version, and up on top is the lazy version. In the ordinary version, what we're looking at is a procedure call, right? So in real scheme, what's the first step in doing a procedure call? Yes? Yes, evaluate all the sub-expressions, the operator and the arguments. And that's what we do. We MC eval the operator. We list of values, which is just essentially map eval for the operands. And then we call MC apply with the actual procedure that we're calling and the actual argument values. Now in the lazy evaluator, the thing that's highlighted on top, we call actual value instead of MC eval. So we're still evaluating it, but you'll see that what actual value does, this is just a little detail, the kind of thing we're not going to ask you questions about on the final, but you should understand it anyway. If we are uniformly turning argument expressions into thunks, into lambda, open paren, close paren, the expression. If we're delaying arguments all the time, suppose we have something like this. Define A of x to be B of x, and B is another procedure that we define. So I now invoke A with some actual argument expression. We turn that into a thunk, and we pass the thunk, we bind x to that thunk, and then evaluate in the new environment B of x. Well, that's a procedure call also. So we're going to turn its argument into a thunk. So now what we have is a thunk of a thunk. In effect, we have delay of something. All right? And that could happen, 20 times before we eventually call a primitive procedure, and then we need the value. So actual value says, evaluate this. Did the value turn out to be a thunk? Force it, and then evaluate that. And just keep doing that, forcing and evaluating, until finally we get a value. Okay? So that's what actual value does. Now, what about operands? In the ordinary metacircular evaluator, we call list of values, which cutters its way down the list of expressions, turning it into a list of values by evaluating each expression in the current environment. Here, instead, we just give apply operands exp. In my lecture notes, I did it a slightly different way. If it confuses you to see things done in two different ways, then just go with the books version. But I don't like the books version because, as you see, it requires us to pass the current environment to apply as a third argument. Why? Because apply is going to take this actual argument expression, and if we're calling a primitive, it's going to evaluate it in the current environment, and otherwise it's going to delay it in the current environment. So either way, we actually need the current environment in eval. So what I prefer to do is just delay it, delay all the operands in eval, and then we can call apply with the procedure that we're calling and a list of thunks. So a list of actual argument thunks. And then if what we're calling is a primitive procedure, we can go through and actual value all of those thunks. If not, we just pass the thunks themselves on, and we don't have to apply a third argument. So I think it's prettier my way. But again, this is the book's way, what you're seeing on the screen now. So what's printed in the lecture notes is a little different. Don't get confused. Okay. Good. Now let's see what happens in apply. Okay. So in ordinary apply, for a primitive procedure, we just call the procedure with the arguments. Very straightforward. Because in ordinary scheme, we have already actual argument values, which is exactly what the primitive needs. So it's really easy to do that. Up here, what we have to do is call list of arg values. That essentially is a map actual value over the arguments. Okay? No, it's not, because we were given argument expressions in the book's version. So it's evaluate. It's basically just like eval sequence, except that it remembers all of them. So it's like list of values. List of arg values is basically just like list of values. We take the expressions and we evaluate them in the current environment, and that gives us argument values, which we give to the primitive. What if it's a compound procedure? Well, in ordinary MC eval, in the apply procedure, we have to extend the environment by binding the formal parameters of the procedure to the actual argument values. Whoops, I lost the A. There we go. And then we use that to extend procedure environment. Up here, we do almost the same thing about extend environment, except instead of arguments, it's list of delayed args. So up here it was list of arg values. Here it's list of delayed args. So we're going to take the actual argument expressions and we're going to delay them all. We're going to turn them into thunks. Okay, and we're going to pass those to the user-created procedure by binding the procedure's formal parameters to these thunks that we just made, rather than to values. Okay, and then everything else is the same. It's eval sequence, procedure body, procedure in this extended environment. All right, just like that. Okay, questions so far? Okay. We're about 90% done looking at the changes in the lazy evaluator. It's called lazy because it puts off evaluating argument expressions until it really needs them, just like lazy people. This change to eval, to not evaluate the argument expressions, and the change to apply so that it either does evaluate for a primitive or thunks for a non-primitive procedure, that's the essence of the change. It's a pretty tiny change. We'll see that there's a few more details, but this is the essence of it. And it makes quite a huge difference in the interpreted language. Namely, things go wrong if you try to do mutation in this language. And so it's a move in the direction of a purely functional version of scheme. rather than this sort of everything for everybody scheme that the real scheme is. Okay? Tiny change in the code, big change in behavior. All right, so this is one of the things I'd like you to remember in the course. This comes up, by the way, quite a lot. Whenever any company comes up with a new version of a program, right, they always take out these advertisements about amazing new feature. You know, now we can do such and such. And the feature may, in fact, be amazing from the point of view of usability, but that doesn't mean it was hard to implement. So, you know, before you're impressed, you should think about, well, what did they have to do to make this happen? Same thing here. It really is a big difference in terms of how the user interacts with Scheme. If we had been using a lazy scheme from the beginning of the course, we would have had a lot of trouble in Chapter 3 trying to do object-oriented programming and sort of simulation of time in the world with time in the program. But it's not much code. So what else is there in the code? So here's a list of arg values, and it just maps actual value over the expressions. List of delayed args maps delay it. So what else? Here's an example of a special form. Eval if is slightly different. Namely, right here, if needs to know the actual value of its first argument, because it's going to choose either the second argument or the third argument based on the true or falseness of the first argument. So it needs to know right now, is that first argument true or false? It doesn't actually need to know the real values of the second or third argument. If the second or third argument is a thunk, turns out to be a thunk, that's okay. So we can just call regular old MC eval, and if we get a thunk, that's fine, we return a thunk. But for the first one, we need not a thunk, we need an actual value, so we call actual value. Oops, what did I just do? That's what I did. Okay. So here's something a little bit different. The read eval print loop is actually a read actual value print loop. Okay? Because you can't print a thunk. That would sort of confuse the user. Once the user asks for the value of some expression, the user wants to know the actual value, right? So here's a place. So if and driver loop are a couple of places where we have to change eval to actual value. So part of the work of doing this that Abelson and Sussman had to do was to go through the whole metacircular evaluator, looking at calls to MC eval and deciding which of them had to be thunked and which of them had to be actual valued. So now we have to actually implement thunks. So we implement delay and force. We don't use STK's delay and force. And this is the usual problem about metacircularness. It's not an STK thunk that we want. It's a metacircular evaluator thunk. The evaluator that the environment that we want to save along with this expression is the metacircular environment, the one with the metacircular schemes, users, variables, not the one with the interpreter's own variables in STK. So we're redoing delay and force, and here's how we do it. So here, let's start with delay. Delay it, expression environment. It could just say make procedure. As we know, thunks are equivalent to procedures of no arguments. But they actually don't do that. They make it a separate data type. So instead of list, quote, procedure, blah, blah, it's list, quote, thunk, blah, blah. Okay? So that's what a thunk looks like. So now we have to have thunk question mark and selectors for thunks. And how do we force something? Well, first of all, we do this conservatively. So it's possible that someone will try forcing something that isn't a thunk. Okay, because either by mistake or because sometimes it is, sometimes it isn't, whatever the situation is, somebody might call force it with a non-thunk. If so, we just return the argument. It's not a thunk, it's a value. But if so, we call actual value, and we pull out the expression and the environment from the thunk and evaluate that expression in that environment. Okay? So that's what force it does. Actual value is a little complicated, and I've lost it. Where did it go? Oh, sorry. No, actual value is simple, but here's a different version of force it. So the original force it was just thunk, expression, value. Here's a new one that does memoization. So now, instead of just thunks and non-thunks, there are three kinds of things in the world: thunks, evaluated thunks, and ordinary things. So if something is an ordinary thing down in the else clause here, then we just return the thing as before. If it's an evaluated thunk, this is a selector for evaluated thunks. It's like catter or something. And we pull out the already computed value. So we don't do any evaluation here. We just pull it out and return it. If it's an ordinary thunk, then, and we're trying to force it, then we compute the actual value of the thunk expression in the thunk environment, call that result. Now we change its type tag from thunk to evaluated thunk. We change its expression into the value. So this is a little ugly. We're changing the value of something. And we turn its remembered environment into just the empty list because we don't need it anymore. We didn't have to do that. It's an efficiency thing. If this thunk is the only reason why we're remembering some environment, then we can let STK garbage collect that environment by not remembering it anymore. So that's the version of force it that has memoization. So you can do it either way, with or without. You really want to do it with, in most cases, for efficiency reasons. And that's it. Ta-da! Now here's actual value. I missed it before. It's in between eval and apply. Actual value says evaluate the thing and then call force it. So if evaluating the thing, if the thing is, a number or a variable name or something, then evaluating it just gives its value, and force it won't do anything. It'll just return its argument. But if it so happens that MC_eval returns a thunk, because it's the value of the formal parameter to some user procedure, let's say, then force it will force that. And force it calls eval again. So if you go look at force it, it calls actual value. Actual value calls force it. So it's a mutual recursion kind of. The base case of it is when we get to something that isn't a thunk, then force it doesn't have to call actual value anymore. And it just returns that thing. Okay? So those are a few more details about exactly how making a delayed object works. You have to understand that. And there are a couple of places in the evaluator that aren't obvious, like in the special forms and in the REPL, that you have to worry about, do I need to know the actual value of this thing right now? In which case you call actual value. But the essence of the change is a little bit of a change to eval, just for the case of procedure calls, and a little bit of a change to apply to handle the fact that we're given expressions instead of values. Questions? Okay. All right, that's really it for this evaluator. I think it's worth your while, even though we're not going to ask you questions about it on the final. It's worth your while going through more slowly in the book exactly how making a thunk and using a thunk are done. Because when you look at it in detail, you're very likely going to have some confusion about the distinction between metacircular scheme and STK scheme. And it's good for you to actually work that through. And note, by the way, an important thing about this is doing this doesn't change STK. Right? STK is an applicative order scheme. So we can use an applicative order scheme to implement a normal order scheme. We could do it the other way too. If what we were given was a normal order scheme, we could invent an applicative order scheme if we wanted to. Okay, so that's important. All of these languages are equivalent in the sense that you can compute anything in any of them. It's just a question of what's easiest to do for a user and what's harder to do for the user. So functional programming, it's easier with normal order evaluation because you don't get into trouble the way Lewis did. And the book does also, if you remember in the book, when they were looking at streams, maybe you skipped it over with glazed eyes, but there was an example about a numeric solution of some differential equation for some electronic circuit, and they got in trouble where they had to explicitly delay something. So when you're doing complicated things with streams that are built on top of applicative order, you do run into these problems. It's not only Lewis who has troubles like that. So normal order evaluation would fix that, but at the cost of losing a clear model for how mutation works. Okay, I will see you Friday, and you're going to bring a pencil.